Okay, so same idea here. So here's the triangle. You can set the vertices, and so I'm going to move. Let's see. So here's say center one, and then center one y coordinate, then center two y coordinate. So let's just put them here and here. So then there's okay. So when you here's angle one as a slider, and so when you engaged angle one, it grabs the triangle and it rotates it around center one. Okay, and then after that, if you engage angle two, it grabs the new position of the triangle and rotates it around center two. That's pretty cool. So this is like a real primitive kind of thing that would be like, graphics in a computer game or something like that, right? So you'd have the mathematics behind this would be some kind of simplistic version of creating, you know, creating some kind of, movement of a character in a video game. Okay? So questions about how this works. So you're going to be creating this, but we're gonna do a lot of groundwork. I'm just not gonna set you loose with this. We're gonna do groundwork in class today and then Thursday to get you ready to do this. So any questions on how it works, right? So you can change the vertices of the triangle. You can move the center or the rotation points. And then once you got them set, then rotation angle one rotates the triangle around the first center, and then angle two grabs it from there and rotates it around the second center. So pretty cool. All right, any questions on how it works? Okay, so let's talk about if we wanted to move towards creating this and maybe you don't have a lot of experience or any with the mathematics of rotations, where could we start? What would be something we could do to make progress rather than being overwhelmed by this kind of sophisticated animation, right? This is pretty sophisticated. So can we boil some important things of this down to something simple to work on first? What might that be? Okay, so for instance, we're rotating, like this first thing rotates about center one. Okay, so rather than rotate about any center, right? Any center, what might be an easier version to start with?
Rotating a point about the origin.
Right. So rather than having the flexibility to move the center anywhere you want, we rotate around the origin, right? That would be the first simple thing to do. And then what should we rotate around the origin? A triangle? What's the simplest thing we could start with rotating about the origin?
Just like a point.
Yeah, point. So let's see if we can come up with a file that just starts with you would, instead of picking three vertices of a triangle, you just pick one point, right? Just pick one point, and it could be anything. And then we'd have some angle, and we would rotate that point would then rotate around the origin. Is such file. This point we can move anywhere. So I can move it to, say, right now it's at 5, 2. I can move it to 7, -1. So now it would start there. I can move it over to the fourth quadrant. So -3, -4. Start here. So no matter how I choose the coordinates of A, then when I engage angle, it takes that point and starting from the point A, takes us all the way around the origin in the circle. Okay, move it back to 5, 2. And then it does, right? Rotates it around the origin, starting from whatever point A is. Okay? Okay, so how do we do this? So you're becoming mathematicians. You're writing some proofs in your other math classes? Have you had proof writing classes? 300? Anything above 300? Or have you not gotten to those classes yet? Have you got second math 300?
I took it like 2 years ago.
2 years ago? Have you taken some proof writing classes since then?
I'm in advanced calc right now.
Okay. What about the rest of you?
I'm just taking it this semester.
Okay. All right, so what does it mean to, so I've got this 0.52, and right now the angle is set at 0.565, and it shows the rotated point. That point rotated about the origin. So what do we think? How are we going to start on this?
It would be nice to know like the radius from the center to the points.
Okay.
Yeah.
All right, so so you're thinking about like this distance right here? And is that the same or just different than this distance right here?
Same.
Same. Okay, so there's a radius there. And so should I write square root of 29? If I'm trying to create this animation where I can put in any values for the x and y coordinates of A, and then the angle will just rotate it. Should we put 29 and 5, 2 like this?
I guess if you want to like generalize it, is that what we're supposed to do? So it'd be like.
Well, does this program generalize it? Does this file
Yeah.
generalize it, or does it only do it for 5, 2?
For all of them.
Yeah, right. It works for. I showed you. It works for any. You can put any point. You can put any coordinates in for x and y, and then any angle, and it will show you that rotated point. So
then the radius would be the square root of x squared plus y squared.
Oh, okay. So, and when you say x, what are x and y? What are those? So where did x and y come from? What would that mean?
They're like the points. I guess points in A is what I was referring to.
The coordinates of A.
Yeah.
All right. So you wanna assign coordinates for point A.
Yeah.
And how should we assign it?
X and Y is fine, I guess.
Sure. Okay. And I'm going to do x1 and y1. Okay. And so we know we can get that radius, knowing that those are the x and y coordinates. We can get that radius using square root. Okay. Anything else? While we're generalizing the situation? Somebody new?
Do you like want to generalize the equation of the circle that it's going around?
Okay. Maybe. So what would that be? So that would just really be, x squared plus y squared equals r squared. X squared plus y squared equals x1 squared plus y1 squared. So that would give you like all points on the circle. So so now we're generalized this point. What about this point? Is this point a specific point, or is it generalized?
I kind of think it can be generalized. Why I thought is like you can make a parametric equation that relates the initial x sub 1 to the new points.
Yeah, right. So
For x.
yeah, that's the idea that like given x1, y1, we're trying to figure out what x2, y2, what this point is, right? So can we call it x2, y2? Let's call it x2, y2. So is that the only thing that this new point depends on, right? So the whole point, like kind of the whole point of this animation is that it's showing us where this point is, right? And is that only dependent on x1, y1, or on anything else?
I think it's dependent on the angle.
Okay. And Donna, where can I illustrate that angle on here? Where can I do that? So you can use the symbol alpha for angle. Okay, so angle is alpha rather than writing that out. So where is alpha? Where is the angle alpha?
It's the angle between the two radiuses.
That I drew?
Mm-hmm.
Yeah. Okay, very good. So we're trying to really the point of this is to determine those, right? So what about that? How do I? So I don't really want to solve the equation of the circle because I'm going to have square roots and I'm going to have square sums of terms under square roots. It's kind of clunky, right? It's not the natural way to do circles, right? The natural way to do circles is not in rectangular coordinates. So I need a more natural way to express x2 and y2. Angel, are you there? Any ideas?
Yeah, I'm there. I'm thinking though.
Okay. So rather than, solving this for y equals the square root of x1 squared plus x2 squared. We talked about efficiency, right? This is not very efficient. Minus x squared equals, y. So this isn't efficient. And the other problem with this is it only works for the top half of the circle. As soon as you get to the bottom half of the circle, you need a new formula, right? You need negative square root. So because circles aren't well aligned with rectangular coordinates is about squares and rectangles and right angles. Well, circles aren't aligned, don't fit nicely with that, and so then that's why you get inconvenient equations and formulas when you try to use rectangular coordinates to express circles. So what's a more natural way?
Polar coordinates.
Okay. So tell me.
I don't remember the formula for them. It's like, well, actually, just kidding. This isn't like radius times cosine theta or cosine something.
Cosine something. Okay, good. And then y2?
Would be r times sine of something.
How about this? Is this a natural way to define things on circles? The definition of cosine, by definition, the cosine is the x-coordinate on a circle, right? And by definition, the sine is the y-coordinate on a circle. So yeah, so when you have circles and ellipses, the natural way to do that is with cosine and sine. And then you also, does it work all the way around? Yeah, and it works as many times as you want to go around. You can keep going around in circles, and it works. You can go backwards, right? So there's huge advantage to cosine and sine for circle over square root approach, or the rectangular coordinates approach. Okay, so she said r cosine something. So somebody knew. What's the something going to be? So what? Elizabeth, are you here?
Yeah, I'm here. I would think that
Oh, you're real quiet.
Oh, sorry. I think it would be like our angle, right? Like
So
the
alpha.
triangle.
So alpha.
Yeah.
Okay, so she's offering up alpha. What about the rest of you? Is that right?
No, or at least not by itself.
Why not?
Because alpha would be the angle measured from, would just be, or it's supposed to be sweeping from the 3 o'clock position counterclockwise. Meanwhile, this is only like from the 10 o'clock position.
So if we used alpha, what would we be getting?
We're not like getting from like the 0, like because alpha would start at the bottom.
Yeah, it'd be like
Missing.
in some kind of like new transformed coordinate system. Do you see that? So this would be like this would be if you did just your x2 would be based on the x-axis being here and here if you did alpha. Does that make sense? I have a lot of erasing to do here. All right, so what instead then? Elizabeth, you want to?
So then we would have to like add from like that, right? So we'd have to add, because it's starting at the 3 o'clock position, right? Instead.
Right.
So we have to add pi fourths, question mark? I don't know. I'm not sure.
So what do we add? Maybe it's more like pi over 6?
Yeah, like pi 6.
What do we think?
Okay. Yeah, I think that would work. I'm sure.
What do the rest of you think? Agree with that?
I don't know if that's the exact angle, but I'm not sure how to find the exact angle.
There's a function we could use, like arctan 2 over 5, probably be the exact angle.
Okay. So arctan 2/5. Everybody agree with that? So we got a pretty big issue here that we kind of talked about earlier. What's going on here?
Using like 2 over 5 isn't generalizing it.
Exactly, right? So when I change the coordinates of A, and when I change those coordinates, is it going to be arctan of 2/5? No. So, actually we don't really actually need, because I've seen how this goes, we don't even really need to say what that angle is based on the point. So we could say, wait, arctan of y1 over x1. Okay, so arctan y1 over x1. But we don't even really need to do that. But we do need something general. We don't need to, or we shouldn't, make it a particular value, right? Because as soon as we change the point A, it changes. So we just need to, it doesn't need to depend on x1 and y1. It just needs to be general. So what can we do? So like theta, right? So it's just, generalizing. Generalizing. It can be anything. So theta. Okay. So let's we've got. All right, we're making some progress. Strong up here. Okay, and so the only other thing here we got is that we just decided that this would be the angle theta. And what did we say? We said x2 is radius times cosine of I'm calling it A now, so A plus theta. And then y2 equals r of cosine of a sine u. And what is our goal again? We're trying to write x2 and y2 in terms of what? So we're thinking we have function mentality, right? Function mentality. X2 and Y2 are going to be dependent on what in this file?
Alpha, or the angle between the 2 points
A.
and the initial point.
Good. Yeah. So how are we doing so far? So what do we have? We have x2 and y2 in terms of r and a and theta. What we need is x2 to be in terms of what a and the initial point. All right, so let's look at the initial point. So what can we say about the initial point that might help us bridge the gap here? So we got to get the initial point involved, right? So there's nothing here about that initial point of those coordinates. So how can we get that involved? What about this?
The initial points can tell you what r is, what the radius is.
Okay. So that goes back to, invoking a square root. And so I think if we stick with polar coordinates or trig, we can kind of avoid that. But what about x1 and y1? What do we know about that?
X1 can be written as like r cosine theta.
Mm-hmm.
And then y1 can be written as r sine theta.
Okay. So now we've got something to bridge the gap, right? Because x2 is in terms of r and in terms of theta, and we need it in terms of x1, right? And so now we got x1 is r cosine theta, x2 is r sine theta. Okay. So how can we? So we need an idea here. How can we, this doesn't distribute, right? It's not cosine A plus cosine theta, right? You don't distribute when you have the cosine of a sum. But we're needing, sorry, this is x, y1. Right? We're needing to get our cosine theta and our sine theta involved, but cosine theta is kind of locked in there. Sine's kind of locked in there. Any ideas? So does cosine A plus theta equal cosine of A plus cosine of theta? Is that true? Okay, it's not true. So,
Angle. There's like some angle addition formula for cosine.
right. So it's like, okay, it doesn't equal that, but what does it equal, right? So what does it equal?
Is it cosine theta or cosine theta times cosine A plus sine theta sine A?
Okay, you're onto it. So yeah, there's an identity
Sorry.
for the cosine of a sum. It's the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. Okay, and then similarly, the sine of a sum is the sine of the first times the cosine of the second plus the reverse, the sine of the second, the cosine of the first. So was that a helpful step if we're trying to get x1 and y1 involved? Is that going to be helpful? Sarah, how will that be helpful?
Because from x1 and y1 we have cosine theta and sine of theta,
Uh-huh.
and they're both like in the x2 and y2 equations.
Okay.
We're able to use it, so that's like how x1 and y1 are now incorporated in
Okay.
our new.
So can you see what to do? So what should we do now in x2? So what is x1? R cosine theta, right?
Yeah, it would be x1 times cosine A
Okay.
minus y1 times sine A.
So y1 times sine a. The rest of you agree? Agree with that? Okay. And then what about y2? So Yasra, how about y2?
Y2 would be Y1.
Y1 is r sine theta. Where's r sine theta going to come up here?
Oh well, so it would be x1
Uh-huh.
sine of A,
Yep.
and plus, and then y2 times.
Y1, right?
Oh yeah, y1. Sorry about that.
It's okay.
Y1 times cosine of A.
Are we making progress? What just happened? So now look, we got the x coordinate of the second point in terms of what?
In terms of A and x1 and y1.
Yeah, that's exactly what we wanted, right? Look, the r's went away, and the theta went away, right? So we didn't need to say what r was, or we didn't need to say what theta was because they went away. Okay, so now I want to look at this and see if we notice anything. So I've got, if you look at x1 and y1, so here I get x1 times cosine A, and this is like really plus y1 times negative sine A, right? And then x1, and then the same two things, x1 and y1, but this times sine A plus y1 times cosine A. Does that ring a bell? This pair of product and sums. Anyone remember anything from your algebra past? This kind of,
Matrix.
what's that?
Something like that. Is it called the rotation matrix?
But this operation, like what is this operation? You see this? So we got this x1 and y1, and the first one we go x1 times cosine A plus y1 times negative sine A, and then The next one, we have the same two, x1 and y1, but this time times sine A plus y1 times cosine A. So that's a kind of an algorithm for something from your algebra past. Do you remember what algorithm that's for? What that is solving, really?
Is that the cross product?
Not the cross product. Okay, good. But we're on the right track, right? But not cross product. Anybody remember? Across the rows and down the columns. Marching across the row, down the column, multiplying and adding. Across the row, down the column. Ring a bell? Anybody?
Is that matrix multiplication?
Yes. Yeah. So what two matrices would we multiply together that would result in these equations? Can we go backwards? So whenever you did this before, you were given the matrices and they told you multiply them. Now we've got a set of equations. Can we work backwards and reconstruct the actual matrices or the equation of matrices and the multiplication that results in these two equations? Can we do it?
I can try.
Please.
The first one would just be x1, y1.
Okay. And you want a row or a column? Column.
And then the second matrix, it'd be a 2 by 2 matrix. Wait, yeah, I think. And then it'd be cosine A for the first one.
Mm-hmm.
And then
yeah, so you got the 2 by 2, right? The cosines and sines. So the question is, does the 2 by 2, is that multiplying in front on this side or is it multiplying on this side?
the second side.
Over here?
Yeah.
And so you remember how when you multiply, you go across the first one and then down the columns of the second one.
So wouldn't it be
Oh, we go on the left side.
What's that?
The matrix should be on the 2 by 2 should be on the left side of the 1 by 2 matrix.
Yeah, because we're gonna go across the first one you go across, and the second one you go down.
What if you just switch the sign A's in that one? Like, does it matter?
Well,
'Cause
it's about the dimensions. It's not about what these are. It's about the dimensions, right? Because
Okay.
this is a 2 by 1,
Yeah.
and this is a 2 by 2. Remember
okay.
this? And so
Yeah.
when can you multiply?
If the second one is the same as the first one.
Right, because we're gonna go across the row, which is the number of columns, and we're gonna go down the columns, which is the number of rows, and that has to match up.
Yeah.
So yeah, we need to do it the other way. So let's see. Let's check it. Ready? So you go across the row and down the column, and you multiply and add. So hopefully everyone at least remembers this, or at some point you did this. Cosine A times x1 minus sine A times y1. Is that what we have? Yep. And what does that equal? Across the row, down the column, that equals
x2.
x2. And then we go across the row, sine A times x1 plus cosine A times y1. So you go across the row simultaneously down the column, multiply and add. So is that what we get? x1 times sine A plus y1 times cosine A. And that equals?
y2.
Look at that. And what did we say? So in order to get this new point, this new rotated point, it was going to be a function of or dependent on A and our initial point. So this is perfect, right? We know what to deal with theta, we know what to do with R. And Richard said it, this is called the rotation matrix, because it has the exact effect that we need. It's going to rotate this point about the origin by an angle measure of A. Okay, any questions on that derivation? It's super slick, right? I mean, it's just like you do this, use this identity, and then you get exactly what you need, r cosine theta, r sine theta, for x1 to plug in, and then you get this super clean equation, right? So no square roots to be found, right? Anywhere. Okay, so now in GC, we want to define this as a function. All the functions, you know, that you've been used to, the independent quantity or quantities have been values, right? So, for instance, z equals f of xy. So this is a multivariable function. You know, you're used to these independent quantities being, you plug in values, and the function gives you a corresponding value. Well, this is different now, right? Instead of all values going in, what's gonna be going in? So we'll have our function called capital R for rotation, all right? And so what kinds of things are going to go into the rotation? What kind of things? It's not going to be just values anymore. And what kind of things is going to come out? Okay, and then another just recommendation when you're writing generic functions is to use dummy variables. Okay, use symbols for let's see. Yeah, so use symbols for the independent and dependent entities that are different than what you're actually going to use when you use the function. So for instance, so this is it's just really helpful to not cloud the issue. So I'll come up here. All right, so for instance, say I was going to define a function so lots, the generic things, f of x equals, say x cubed plus 2x plus 1, okay? Well, let's say you remember we did that, the composite function, the 3D composite functions. And so let's say I want to write z as I want to graph the dependent on the z-axis and the independent on the y-axis, or I want to graph this function, this relationship, the dependent on the x-axis and the independent be z. So do you see that by defining the function this way, it kind of clouds the issue for how I want to use it, because you get this idea in your head that this has to be x. Does that make sense? So it's kind of a smart thing for just ease and convenience and efficiency, is to just name, when you actually define a function, use something totally different than what you're going to be using what symbols you're going to be using when you're actually using the function. So for instance, I could just use c. Was it 2c? 2x? Whatever it was. Right? So use dummy variables that they can be related to the things that they are, but they're not going to be what you actually use when you use the function. And so then I got z as a function of y, and there's no x, y's, and z's in my function to confuse me as to what's happening here. And then I can graph the dependent on the x-axis and the independent on the z-axis, and again, so this is the idea of a dummy variable. And so I want to do the same thing. So what are we, when it comes to the angle, what are we actually going to use? Where is it? So here's the actual file. Let's give some space for it. Okay, right there. So when it comes to actually, entering in angles and having the function execute, what do we call that? That's a really easy question. Angle, right? Angle, right? So I've created this character string angle, and that's taking on the value of the angle of rotation. And so after I define the function, I start to use it, that's when I'm going to use angle. So when we define the function, let's not use angle. But then when we use it, when we actually plot the point, we'll use angle. Make sense? This is good for efficiency, okay? And then the x1, y1. The x1, y1, this point. When I use the function, what symbol am I going to use when I use the function? A, right? So you can let capital letters stand for points, and that's going to be part of your function here. That it's not just going to be values, but now you can have functions that have a point, right? So we don't want to use capital A in the function. So then we know that when we're using the function, we're going to use angle and A. And that will execute whatever the rule is on angle and A. All right, so I'm going to break you up into groups, and you guys are going to see if you can write this file. So what does that mean? And so this was kind of misleading here. You define the function, you have the function notation, then equals the rule. Okay. So you need to define the function, and then you need a line that uses the function to plot the rotated point. And then if you change angle, it should go around. Does it make sense? So to get we've done these like a 2x1 before. That's Control 2. If you go in the math menu, somewhere there's a I thought there was a in the menu there was a way to do 2x2. Keyboard shortcuts. Jeez, I don't know. I thought it was right there in the math menu. What is it? How do you do a shift 2? No.
It says it's Control Shift 2 for 2.
That's what I just did. There we go. So where did you find that? I thought it was in the math menu.
Mine was in the math menu.
It's not on the math menu, and I knew it was there, but it's not showing up. Anyway, Control Shift 2 gets you a 2x2 matrix, and just Control 2 gets you the 2x1 column matrix. Okay, so let's see if you guys can successfully write this file. Okay, you're going to work together. Did we have some progress? How does it? Yeah, it just seems that there we go. Okay. So Donna, you're the first one in my viewfinder there. How did you come up with something productive here? Something that works?
I did capital R of, so for the function, capital R of capital X comma little a equals.
Okay, and how did you come up with those symbols?
Well, since we were using capital letters for points
Okay.
in the example point, I just used a random capital letter
Okay.
for the dummy variable,
All right.
and then A for angle
Okay.
for the other dummy variable.
Yeah. So that's what I picked for my file as well. I mean, when I've done this before, the one that I showed you, I think that's what I picked. Okay. So and then what did you guys come up with for this? The rule for this function?
I did the 2 by 2 matrix.
2 by 2 matrix.
It's the rotation matrix.
Okay.
Cosine A.
Okay.
And then negative sine A.
Okay.
Sine A. And cosine A.
Oops.
And
Yeah, there we go. All right.
then move to the right outside of the matrix.
Yep.
And you multiply by capital X, or our point.
Okay. Is that the whole thing?
Yeah.
Okay. What about the other teams here?
You have 0 minus sine A in there. Not
I know.
negative.
Is that different or the same?
I mean, it's the same, but
Yeah. I saw that too, and I thought, oh, it's the same, so let's take it. But yes, we should get rid of it. There we go. There we go. Okay. The rest of you agree? Other teams agree with that? You came with something different? Disagree? Blank stares. All my life, blank stares. Even through Zoom. Not only in the classroom. So, you had something different, but you like this. You had something different, but you like yours better. You didn't have anything at all. You had this. So, other teams. Angel, were you in a different group?
Yeah.
Than
we
Donna?
were-
How does this compare to what you came up with for the rotation function?
It's similar to what we had. We were just kind of confused on the format overall, but it makes sense to me now.
Do you agree with this?
Yeah.
Okay. What about the third team? Ashley, were you on one of those two teams or a different team?
Angel's team.
What's that? Who's
She was on my team.
she was on Angel? Okay. What about Elizabeth? Were you a third team or were we in one of those? Same thing.
Yeah.
Okay, and so now, so if I hit graph, this will plot the point. Is that right? Well, I can't hit graph. It's not showing up blue. What's wrong?
You have to have like y equals something for it to graph.
Okay, that's the general idea, right? So this is just defining the function, and so this isn't going to plot anything. It's just defining a relationship, right? It's us telling GC what we want this function notation to mean, right? But it doesn't plot anything, doesn't do anything. Okay, so what's next? Am I ready to plot the new point?
Yes, we are.
Okay. Richard, what do you think?
So it's going to be capital R, parentheses, A, comma, angle.
Oops. Like this?
Yep.
And what will that do?
It'll graph the points based on the rotation of the angle that
Okay.
we choose.
Should we try it? Seems to work. Now, so starting at 5, 2, seems to work. What's missing from what I showed you before? In this file now.
Is it the initial point?
Yeah, so I left the initial point sitting there after we start moving the new point. So how can I plot the initial point?
Would capital A just work?
Right, so there's kind of two major things with GC. You define things, and then you tell GC to plot them or calculate them, right? And so, yeah, if you just say A, it's just going to do whatever A is. Well, A is a point, so it's going to plot the point. Let me zoom in, zoom out. All right, so did any team do it successfully before we gathered back together? Any team?
No, I got like 90% of it.
90%. Yeah, so we got to define the function, and then plot the point using function notation, the change point, and then plot the original point.
Oh, I guess 66% then.
Okay, any questions? Okay, so your next assignment will be then, so initial point around a center. So now I'm going to choose a center, -1, 3 instead of 0, 0, and then the angle will rotate the point around the new center instead of around 0, 0. So once we get this, we're dangerously close to being able to write that the first file I showed you with the rotating triangles. It just is a matter of several lines, but it's the same concept over and over again. So this is what you're going to work on now. So instead of rotating around the origin, you're going to have a new point C, and that can be anything. You're going to rotate the point A around C instead of just 0, 0. And what I want you to do is I want you to go back and don't try to take the old rotation matrix and just tweak it. We want to go back and we want to do the math derivation in writing the way that we did in class today. Does that make sense? So we derived the rotation matrix from scratch. I want you to start over and see if you can do it again now with a center point, any value. Call this like XC, YC. Instead of just 0, 0, this can be any point XC, YC, and then but start, like I said, start from scratch, do the math, use the identities, and don't try to just take the rotation matrix we had and do a little tweak to it, okay? Because unless you have really good foresight, that you won't be able to tweak it right. I mean, so you might have an idea how to tweak it, but it won't be right. So we're going to start from scratch and start over and try to build this file, okay? So that will be your assignment.